First, I just want to say it's really cool to be here at Blue Tavern doing this. I've been here a bunch, usually in the role as a maybe possibly slightly drunk musician. I'm not going to be doing music or songs or be drunk tonight, but I'm really excited to talk to you about this. The title is really boring. I actually signed up for this a couple months ago, then had a baby, and totally forgot to come up with a good title. So it will be more interesting, I promise.
Chris, hide that bottom thing.
Oh, thank you. All right, so I actually have a background in ecology, conservation biology. I studied fisheries at Auburn, so I kind of took a weird path into remote sensing. Basically, I worked at a lot of field stations. How many of you in here are some sort of scientists? Okay, cool, so a little over half of you. How many of you are in natural resources? Quite a few. If you've worked in a natural resource office, you know that in the small field offices, you don't usually have a remote sensing expert or a GIS expert. It's just whoever knows how to turn on the computer. That was me. I studied ecology specifically, so I never have a job where I sat behind a computer. Now I sit behind a computer every day, but I actually really love it because it allows us to address so many ecological problems. And kind of the idea for this talk actually was unrelated to ecology. I thought of it with the Artemis II launch. And any of you get excited for Artemis II? All right, yeah. It was pretty awesome. We're in very weird, divisive times, and it struck me how excited people were for NASA again. Like, if you look back in American history, NASA was a driving force for innovation, and suddenly people across the political spectrum were like on Facebook and other social medias like, yeah, NASA's back. Which, don't get me wrong, it was really cool to see that excitement, but my thought was like, well, where the hell? It hasn't been gone. They've been doing other stuff. So I wanted to highlight some of the other things NASA has done, even though I think like that mission is awesome, but the most studied planet by NASA is Earth. And we can learn a lot from their observations and a lot from other agencies like NOAA and the US Geological Survey. So that's what this is going to be about, and we'll just jump right into it. So what the heck is remote sensing? I wanted the official definition from one of the agencies I work with, the US Geological Survey, and they say detecting and monitoring the physical characteristics of an area by measuring its reflected and emitted radiation at a distance, typically from satellite or aircraft. That is actually 100% true, but probably way more advanced than me for this talk. So really you can just think of it as measuring the environment from a distance using sensors on things like planes or satellites and a lot of other things. If you look here, cars, weather balloons. For this talk, we're going to focus mostly on satellites. These major satellite missions are what I work with a lot. There's also these meteorological satellites. I'm not going to talk about those as much. It's not because they're not important, but I just don't work with them too often. And also, maybe I'm being optimistic here, but part of the reason I want you to learn from this talk is that you go out and support these tools, and I hope that no one is considering cutting, basic satellites that get us weather data. But that could be overly optimistic. So remote sensing has no direct measurement. We can cover large areas, and it's a pretty cool tool. So how does it all work? Well, first we have satellites, and they're orbiting around the Earth. So there's a couple different orbit types. The two main ones that we need to know for the context of this talk are geostationary, so that's on the left. And if you look, you can see that the satellite is orbiting the Earth at the same speed the Earth rotates, which means the view it has of the Earth is always of the same location. Polar orbiting, on the other hand, kind of rotate from pole to pole. They're going around while the Earth spins underneath and scanning, so they can observe the entire globe, with some exceptions near the poles, but they get less frequent observation. So there's trade-offs between these two satellites. I work with a lot of polar orbiting satellites, and there are a lot of these. So this is infographic NASA did showing there just the NASA constellation, I believe. If you look on the back, those are ghosts, and they actually have a really wide orbit, so it looks like they're shooting away from Earth, but they're actually, if we have this image in 3D, they would eventually come back around and front like that. But the point is there's a lot of them, and they all measure different things. So again, we can cover wide areas, we can access hard to reach areas like the poles or sub-Saharan Africa, and we get regular revisits, so we're getting data collected consistently over time, and it's not intrusive. So the satellites I work with tend to be from NASA or the US Geological Survey, and the really cool thing about them is they are free to literally anybody in the world. But what are these things measuring? I think that's another thing we have to understand before we get into the cool details. So this is the electromagnetic spectrum. Raise your hand if you're at least vaguely familiar with it. Okay, good. This is a science club, so I expected a lot of you know it. But basically, you can think of radiation energy, and it exists in different wavelengths. There's probably a lot of musicians in here as well. So think of your wavelength in a musical note. It's a similar concept. We have longer wavelengths to the left, shorter wavelengths to the right. And what we can see is just this little part in the middle. That's visible light. If we work to the left, we can get into infrared. That's great for looking at things like plants or fires, sometimes even mining. I couldn't find a rock icon, so I just put a pickaxe thing. Microwaves are great for topography, and I've seen some papers where oceanographers use them for wave patterns. Radio wave, I totally blanked on putting an example in there. As we go up into ultraviolet, we can get into clouds and snow. And then we have these pesky ones to the right, X-rays and gamma rays. I guess in theory you could use those for remote sensing, but when we talk about remote sensing in the literature, we're usually talking about remote sensing of Earth. Our atmosphere absorbs most of these rays, so there's nothing to bounce back to the satellite. So those are usually used more for interplanetary studies, super cool stuff, but I don't know anything about it, so we're going to ignore those for this talk. But let's get into the fun stuff, because we don't want to get weeded down in all the nitty-gritty science. So let's do what I do, and we're going to work together to find a fire using an image from remote sensing. How many of you have flown into the Tallahassee airport? How many of you have done that between maybe February and May, and you see fires everywhere? Or if you haven't, have you driven through the national forest or north of town and you've seen where they've been burning? So put that image in your head, and we do want a little bit of participation. So if you were going to look at a satellite image, what would you look for to find a fire?
Smoke.
Smoke would work. Maybe. We're going to go to the image, we'll find out.
Light.
Sometimes you could see a little red dots where the fire could be. Sometimes, especially at night.
Yeah, so the actual visible light from the fire.
I also said light from the fire.
Okay, Bronwyn up front said light from the fire. Kim's heat is one way. Kim's is good for active fire, when the fire is actually burning. What are you thinking?
Black.
Yes, black. So that's what I do. A lot of my work is for fires that have already burned. So everything we mentioned will work, but I don't always have that. But we're going to start with an easy one. This is the Biscuit Fire in Oregon, and we have a wonderful image. We all probably agree on where the fire is, right? We could trace this out. But if we had to actually define this for firefighting purposes, or maybe estimating the amount of timber that burned up, it would get a little tricky when we get up there, right? Because we're obscured by clouds. So there's all these issues. And this also is a fire that had pretty well-defined edges because it was burned up to fire lines that were already in place. It's not always that easy. This was the Biscuit Fire in Oregon. Their fires are really severe. Usually they're more severe than southeastern fires. What I mean by severe is how the fire affects the vegetation content. So you get a nice black. I work in the southeast, and it's not always that nice. So this is St. Mark's, south of Tallahassee. Who wants to tell me where they think the fire occurred?
The brown.
Trick question, it's not there.
It is there. Well, the fire's not there, but it was there shortly before this. Bronwyn's brave and says brown. What? This brown?
Light brown.
That brown. Okay, so yeah, we can be fooled sometimes. In this image, they're kind of a different shade, but depending on atmospheric conditions, they're not always that way. But that other lighter brown is actually wetlands, and you can kind of see that if you pull up a wetland map. So it gives us a little bit better idea of where fire was. But what if you don't have the wetland map, or you don't know the area as well? Like most of us have probably been through St. Mark's. What if I'm looking at somewhere in Arkansas?
I guess you can find areas tell it was a fire burn as opposed to just normal decay?
Yeah, so he's saying we can find areas that have burned instead of like normal decay. The reddish brown in there probably is that. But if we were unsure which shade of brown indicates a fire, and knowing that these satellites visit the same spot over and over, is there anything anyone can think of that would maybe help us discern which brown is fire, which is natural vegetation color or decay?
Change?
Yes, change. This is like one of my bandmates and best friends. I swear I did not plan here to answer all these questions. I didn't even know she's coming. So yeah, we can look at change.
I'm just a nerd.
And then we get a much clearer idea of where the fire was. So I forget the exact numbers. This was about, I think, 9 days apart. Pre-fire, post-fire. So you'll notice not much change with the brown, but change from green to brown.
Yeah.
So that makes it a lot more obvious. So when we do this remote sensing work, there's so many different ways we can approach it, and we can get more detailed answers. But so we've got difference before and after. What's another thing that we may not be considering? And think back to when I showed you that spectrum. These satellites can go across the spectrum and look at things not just that we can see with our eyes.
CO2 content, IR?
Yeah, so he says CO2 content or IR. Basically, what I think what you're implying is we can actually look at things that are not visible to the naked eye when we just look at a raw image. And that brings up one of my favorite things to argue with people on the internet about, false color images. Are they really false? No, but we'll get to that. So to understand false color, we go back to that spectrum. In the middle, you see visible light. That's what we were looking at in the last image. What I'm going to show you next is going to use green from visible light, and then go into these IR ranges. And the image is going to look a lot different. Oh, forgot to look at my slide. So no, this image doesn't look a lot different because I'm showing you in true color first. And you can see here, it's intuitive, it looks natural, but it's hard to tell water from those dark patches, some of which are burns, some are actually flooded fields, and you can tell the difference between developed area. When we put it in that false color I just told you about, first I just think it looks really vibrant and awesome, right? Like I do have pictures like this up on my wall, but you'll notice some changes. So in the previous image it was hard to tell burning from water, and now burning's red, water's blue. So we can tell those sugarcane fields from the wetlands. But developed areas are a little more obscure. They're down there in that pink or purple. And if you don't recognize this, this is the southern part of Florida, below Lake Okeechobee, where we have a lot of sugarcane. The city you're looking at is like West Palm area. So you can use all sorts of different false color images, and we're only going to go through a few. But this one, I think, just looks stunning. Here we're using green, red, and near infrared. These are really good for distinguishing vegetated areas from water and development. So you can kind of get the point. We have all these different wavelengths. We can combine them to see things that would be harder to discern without it. And I was actually a little misleading with this original photo, because this does actually have, I think it was the IR band that gives a little bit of a magenta to the burn scar. So in the true raw color, or true color image, it actually wasn't quite as obvious. So these images aren't false. Note that the name is false color, not false image. We're basically just using colors we can see, red, green, and blue, to perceive things that our eyes couldn't see, like infrared. And that's important because they can help us discriminate between different things. People get so hung up about this, like, well, it's fake. And I tell them to go turn on the Weather Channel or however you get your weather and look at the precipitation forecast. You're going to see green, orange, yellow, then walk outside and look at the clouds. Are they green, orange, and yellow? No, but we just all accept that as normal. That is really a false color representation of something we can't see, which is the amount of rain. Same idea with X-rays, right? We can't see X-rays as grayscale. But when we put them on a film, they appear in the visible light. So that's all we're doing with these images. People get really hung up. I think part of the problem is because now you have stuff like this. I don't know what this is. Someone tagged me on Facebook and said, can you explain this satellite image? I'm not 100% sure it is a satellite image. It could be AI, or it could just be a really jazzed up satellite image. It looks like the post said it was showing how wet Mississippi is. Mississippi does have a lot of rivers. We do have satellite tools that let us look at floodplain and when they flood, but it is not water from Pensacola to Biloxi. I think there must be like a soil moisture component or something here. I'm not really sure. I don't particularly like this image. I think this is why we get distrust in some of our images. But I do love that they labeled that guy down there appropriately. So it gets points for that. So back to our St. Mark's example. You know, when Bronwyn mentioned change, we got a pretty good idea of where the fire is. We had to pull up 2 images. We could also just look at the after fire image in false color and get the same thing. But there's even more that we can do. We can actually take ratios of these different wavelengths and get really cool stuff. Like here, we're looking at NBR, which stands for normalized burn ratio. We're taking wavelengths of different light to really find burned areas. And now you can see it really pops. So this is just one example of remote sensing. This is what I think about a lot during the day. We kind of did that manually. So we're really not getting the advantage of this technology because it takes thousands of hours to have someone sit there and digitize that. So my job at Tall Timbers, which for those of you who don't know, Tall Timbers is a research station and land conservancy north of town. We specialize in fire ecology and getting properties into conservation easements, and we are widely considered like the leading place for establishing prescribed fire as beneficial. So got to put a plug in there. But anyway, my job is to try to map, using these satellite images, fires across the entire southeastern United States. And it's pretty fun. We use a lot of the same things, except we're just teaching a computer to do the work we just did manually. So we know these polar orbiting satellites orbit around from pole to pole. They're sort of scanning. And what I do is I get an image every 8 to 16 days. This image, there's not much fire activity going on. This is Tallahassee, kind of south down to like Apalachicola. You can see those wetlands along the river kind of look like fires. This one's a little cloudy, not much fire. We keep going through. Sometimes you get literal shit images like this where they're just not helpful. They could actually be non-helpful. They can give you false positives. And now you see there's below Lake Talcum, we're starting to see fires. And does anyone want to guess if this is true color or false color? False. Yes. Okay, good. We're all learning here. Keep going on, and by like March, you actually get really good views of these fires all over the Apalachicola National Forest. So we take those images. We have called the image stack, so they represent multiple points throughout the year. And we're going to use a statistical method called boosted regression to kind of generate a burn probability for each of those. So where you see green, the value is 0, that means we're very confident there's no fire. The number ranges from 0 to 100, 100 being we're 100% certain there was a fire, and you know, in between that kind of intermediate confidence. And then we can basically, we have the whole stack, and we just take the maximum value in any area, so we can get a final estimate of where areas burned just in that year. And it's getting a little technical here. I want to talk about the boosted regression just a bit to help you understand like how we automate this. But basically, yes, question.
So when it says burn probability, it's not saying like the probability that it will burn. It's the probability that it already burned.
Yes, correct. So the question, if you can hear, was the burn probability, Brian was asking, is the probability that it will burn or that it has burned? And there is a lot of research where people do risk assessments where they're trying to provide a probability that something will burn in the future. I don't do that. Our probability is looking in the past with like how confident is it that our statistical model is accurately assessing this is burned. And we provide these, I'll get into why we want to know where fires occurred after the fact in a few slides. But, so yeah, excellent question. And to kind of train our models, we basically do what we all did together manually. We find known fires and we drop points. So where there's red, we're saying that burned. Where there's white, we're saying there wasn't a burn. Then we put it into a complicated statistical model. So each of those points, we know what the satellite data, so those wavelengths look like at any given point. And there's usually a difference between burned and unburned. I mentioned we use ratios of wavelengths a lot. That's what you're seeing here. NBR, which we use in our example, features in here quite a lot. But the point is, I don't want to get bogged down in the weeds. If you want to talk statistics and model building with me after, come find me. But for this talk, you should just know by doing this, we're able to automate this process. And here's kind of our important variables. So you'll see NBR on there again. It's very important. NDVI, so one of you is talking about like vegetation, greenness, that effectively measures that. And then we get something that looks like this. We've got a good estimate of fires, but it's a little sloppy, and we use some geospatial processes called smoothing and sieving. Basically, we just fill holes, and if there's little salt and pepper things less than 10 pixels, we group them out. We get a pretty good estimate of fire. And I do that for every single tile in the southeast, so these satellite data and images come in tiles, and I stitch them all together, and it gives us an estimate of where fire occurred across the entire southeastern United States. So why would we want to do that? The fires have already happened last year, right? See, a lot of people don't understand the purpose there, but the reason we do that at Tall Timbers is because it can be useful for things like Kim here does work with all sorts of different endangered species or threatened species. They need fire for their habitat to persist. So if you're a biologist, you can use these data and say, where have we recently had fire? Where can I go look for gopher tortoise, whatever, you name it. Air quality people really like these data because we set our legislation based on smoke. So you can model smoke coming out of here. What are some other uses? Climate change. So we know from research at Tall Timbers that prescribed fire is really important to reduce wildfire risks and to promote species biodiversity. But we have limited weather conditions in which we can do that. So this is getting out of my expertise. I'm not a climate modeler, but people can take these fire data, pair it with climate data, and say, okay, here's the climatic conditions we need to burn. Here's how those conditions are forecasted to change. Uh-oh, we might not have as many burn days. That tells us we need more funding for burning so we can get it done. So there's so many applications. And again, I would like to, I'll hang out after if you want to get into specifics, but I'm just using what I do as one example of remote sensing. We're going to get into some others that are pretty relevant to Florida, so I don't want to dwell on this too much. But we can do other cool things too, like we talked about burning severity. We can take the fire data I produced, and this was done by my colleague at the US Geological Survey, and he actually went out in the field after fires, and like you were talking about looking for chars and scorch, he measured those. And there's basically a metric called the CBI, the Composite Burn Index, that tells you, for measurements on the ground, how the vegetation was affected by that fire. But then he paired it with our data and wrote a model where we can look at the satellite signals and kind of estimate what the CBI will be, even if you didn't go measure it in the field. So it's a really cool way to kind of, collect data or create data over a wide spatial area that would take a lot of person hours. But it does come with some error. I also take these data, and it's really important to understand how fire is not just happening today and yesterday, but in the past. So we stack all the years, and we can find out in any given pixel how many times that's burned in the last 31 years. So if we're looking here, Tallahassee is in the bottom left, and you can see to our northeast we have a lot of fire in the Red Hills region, and southwest tons of fire with Apalachicola National Forest. And in any remote sensing question, there's always limitations and issues you have to deal with. Ours, if any of you have seen an area that burned, then you come back a week or 2 weeks later in the growing season, you know it greens up really fast. So I want you to focus on that burn unit. This is before it's burned, now it's burned, and so it burned at the end of May, and by October it's completely gone. So there's a pretty short window in which we can detect these with satellites. Consider the satellites I use are passing over every 8 to 16 days. And we can actually measure that to see how quickly they come back. So here we're using NBR again. It's widely used in burned area mapping. And you've got this like cyclical pattern. That's because NBR is looking at vegetation, and that changes seasonally. When you get to here, we have a fire, and you see that drop-off. Those drop-offs are what our statistical models look for, because that means there's likely a fire. But you can see in just 2 or 3 months it goes back to that sort of cyclical pattern. One way we can get around this is by incorporating more images. The European Space Agency actually collaborated with NASA to build satellites that function in tandem with ours. They work together and split the orbit, so we get an image every 2 to 3 days. But keep in mind that like international cooperative efforts like that take coordination and time and commitment. And then we also have a lot of clouds down here, even though it's a sunshine state. So with that rapid green up and cloud cover, what you're seeing here on this kind of seizure-inducing thing is the false color image, then our burn probability, then our burn classification running for 2022 all the way to 2023. You can see there's a lot of clouds. So we put those all together. We can have some error. We're working on it. Our potential solution, like I said, is to use European Space Agency data in connection with NASA and USGS data. And the orange at the top just shows that when we combine those two together, so each column is a different year. And the bottom row is just using US satellites, and the top row is when we pair them with European satellites. Or sorry, I said that backwards. Top row is just our satellites, bottom is European. And you can see we get a lot more images, which means more chances of finding fires. So this whole idea of remote sensing is like, we're going to find an image, we're going to find what wavelengths differ between the things we're trying to identify, and then we're going to go at it and we're going to find all these problems, and then we have to think of a clever workaround for that. So it's a lot of fun. That is what I do on a daily basis, but you know, I mentioned in the Facebook ad for this and kind of leading up to the talk that I also wanted to not just focus on what I do. So this is a little weird. As a scientist, I almost always present my research. I think that's important. I'm actually usually very reluctant to present other people's research because it's their work. I don't want to misrepresent it or have people think I did it. But in this case, I wanted, this is almost more like a small literature review. And the reason for that is the satellites I just talked about are only one of the many you saw at the beginning of this slide. And they frequently have been coming up to the budgetary chopping block. And like I said, everyone's all excited about Artemis 2. Most people don't even know that these NASA and NOAA and USGS missions exist, or if they do, they don't know how useful they are. So my hope with reviewing some of these other applications is that, you know, it generates some support for these technologies. And you know, on the topic of being a science advocate, you know, I know we have a lot of scientists and highly educated people here, or non-scientists, they're still smart and educated. When I was defending my master's, one of the committee members asked me the question, like, what is a scientist's role in advocacy? That's a terrifying question to get when you're like 21 years old or 20, whatever I was. But I kind of used a cop-out. I was like, I think that, like, the first thing I'm going to do when I get this degree is try to get a job. And I think whether or not I advocate depends on my job, which is true to an extent, right? Like, if you're doing peer research, the data should speak for itself. If you're working for a government agency trying to address a problem, you interpret the data, and then you have to like use that data to come with a solution. But what we're finding ourselves in now, and this is not just remote sensors, this is nearly all scientists, we're no longer in a position where we just have to advocate for our science, we almost have to advocate for the ability and the money and the technology to do science. And that's really scary. So that's why I want to talk about other people's work. We were talking about fire, we're going to go fire adjacent here. This is an air quality study that my supervisor did, looking at sugarcane burning in South Florida. And basically there are these particulate matters, these forms of pollution, we call them PM2.5. It just means it's really small particles. They're really bad for your health. They can lead to cancer, asthma, and all sorts of things. They are released naturally by fire. But in South Florida, even though tall timbers really supports prescribed fire, the prescribed fire in the sugarcane really doesn't have any ecological benefit. It really just so sugar companies can make a little more money. It makes the harvest more efficient. But it generates a lot of smoke, and a lot of that smoke tends to go into low-income or minority communities. So what my supervisor did before she was at Tall Timbers is she kind of measured that pollution. And what you see on the left is like the average level of that pollution. What you see on the right is if you measure that pollution during burning season and take the difference. So between these two images. So warmer colors mean there's a whole lot more pollution here on average. Cooler colors mean it's a little less. And what you see is around this Everglades agricultural area, here, you get a whole lot of pollution. And actually what they found in a paper, and then they looked at mortality and public health data, is we have about 400,000 acres that burn. They emit like 5,000 metric tons of this pollution, and it does actually increase deaths by 1 to 6 people per year in the state of Florida. So it's just like, sad story, but a cool application, how you can use these tools and actually improve not just the environment, but human lives. Another thing, and I also should mention, I try to keep these topics specific to Florida because, maybe you want to call representatives or something. So Florida is also an agricultural state. We all know that. I went on FDACS, our Department of Agriculture and Consumer Services, and learned that about 14% of our gross domestic product at the state level is related to agriculture. And a really big use of remote sensing is estimating crop yield, not just in Florida, but actually around the world. Now, why is that important? I am not an economist here. Economics and ecology, they have the same root word. It's from like Greek oikos, like the yogurt, meaning how. So there's some relations. They're both fields where you're studying competition and scarcity of resources, but economics is a whole other thing. So I'm not going to get into the very specifics of it, but the reason we want to know what's going on in other parts of the world is farming is an industry where there's often very little profit margin. So if the market gets saturated because someone in the southern hemisphere is growing too many tomatoes, we try to sell tomatoes after our farmers lose money. But what we can do with remote sensing is scan that whole globe and actually get a pretty accurate estimate of how much of each crop every country is going to be producing that year. And then if our farmers are aware and educated, they can actually reach out to like FDACS or the U.S. Department of Agriculture and use that to help plan how much they're going to plant. And this graph is just showing you the number of papers by different satellites. The black line is the total number of scientific papers. Each different shade of blue is a different satellite, and how that's increasing over time. So you can see in like the last 10 years, that's 2020 there, so I guess the last 5 to 10 years, there's a huge increase. Basically, there's a big interest in using this technology to help guide our farmers and make it so they can make money. And I should note that these two shades are NASA satellites. The one on the left is from the European Space Agency. Kind of the same thing here, just breaking that down by crop type. Again, you can see there's a lot more publications on monitoring these crops. So this is something that's really important to you as Floridians. Even if you're not a farmer, it drives a large portion of our economy. And this is just an image, another false color image of farms. And because our agriculture is very monoculture driven, actually we can classify it pretty well. So we can combine these spectral data, whether we were talking about earlier, with things like soil moisture and temperature and rain, and that kind of drives our models. But there's other uses in agriculture, and this one is relevant today. Agricultural pest forecasting. Ta-dum, screwworm. Has anyone watched the news recently? Yeah, so we probably all know what screwworms are. I'm not going to go into that. But they are harmful to livestock. They do infect humans, fortunately rarely. But the point is, like last March, I was doing my job. We actually got paused while federal funds were, who knows, we were figuring stuff out. But this paper came out in July of 2025. It was called Emergence of New World Screwworm in Central and North America. Or sorry, re-emergence. So if you look on the upper left, that was pre-remote sensing days when we started eradicating this thing in the 50s. And each of those lines is another couple of years. You can see how the range has shrunk down to where we pretty much only existed near Panama. Now it's coming back. The map in the upper right pane is basically showing you suitability for this species. As you can see in the pictures, literally lays maggots that burrow into the livestock. So it's pretty cool that people were researching this. I don't think it's cool that the office that managed this pest was shut down. So how did they do this? They took densities of livestock. These are spatial data, but they're not remote sense. As far as I know, we're not yet counting cows and sheep with satellites. But they did have spatial data, then they matched that with climate suitability. I'm doing a little bit of a stretch here because the authors of this paper actually aren't remote sensors. They pulled climate data that was generated by remote sensing data, but I kind of want to show that these technologies and these papers kind of have a trickle-down effect, but you don't need to be a remote sensing expert to use climate data, just like a biologist monitoring lizards doesn't need to be a remote sensing expert to use my fire data. Combine all those, and that's how we got this risk. So, really useful information, probably wasn't listened to. I talked a little bit about endangered species. I don't really like this infographic, it's too dark, but it's what the author provided. But NASA has really cool satellites, you'll see them a lot. They actually monitor, they detect bright lights in the night. In this particular study, they're looking at light pollution on beaches, but I've seen them used for like fisheries enforcement, sting operations, where they can tell, well, there must be like a spawning ground there, so we get a lot of lights. They can be used to count oil wells with the little flares that burn out the excess gas. They can be used for emergency management after a hurricane. A couple of years ago, I should have put in this presentation, I pulled the nightlight data after some of our major storms, and it was crazy, like the whole peninsula just goes dark. So there's a lot of uses. In this case, the red bars that are kind of hard to see are sea turtle nesting densities for 3 different species: loggerhead, green turtle, and leatherback. I have had a varied career, so I did do 2 years of sea turtle time, so I'm a little interested in this. But yeah, so just another use showing you that the more light there is, the fewer nests there are. And these are sometimes things we know at the small scale, but to show that the pattern holds true at the spatial scale is often what politicians and people that actually set our rules and policy are looking for. Ocean pollution, that's another big topic here. Probably everyone in this room is familiar with the Deepwater Horizon oil spill. This study was done by a bunch of people, including Ian McDonald, who's at FSU in, it was oceanography, I think it's Earth, Ocean, Atmosphere Sciences now. Anyway, this one's interesting because in the beginning I talked about how we were going to mostly focus on satellites. They use aircraft and satellites combined. And I wanted to include this one because it's directly relevant to the Gulf Coast, but also demonstrates another one of our techniques. Because the planes are flying lower, they can get a little more detailed view, but they can't cover as much ground. So you can see on the bottom picture, those long, colorful, false color image bands are taken from an aircraft. The entire image underneath is taken from a satellite. So the aircraft collects data that were then calibrated to data collected by boats on the water, and then they calibrate the aircraft bands to the entire satellite image, which gives you something that looks like this. So there's the satellite image, and then on the bottom you see they were going for oil slick thickness. What they did find is there was a lot of error. I mean, that's kind of inherent in this type of research, but it's still useful because you can get data like this, I mean, really on the fly. Like as soon as the satellite passes over, someone can download and produce it. So even though we always want more accurate data, the immediate ability to get something that's still fairly accurate is extremely beneficial. And all they recommend in their paper is like, don't use the absolute values, let's just put in categories. And I thought, you know, sometimes remote sensors overthink things. I thought this was actually a really easy solution. But that brings up like more questions. I mean, I could keep going on. There are a bunch more examples. I was told to be done by like 5 minutes from now, so we can have time for questions and for the band to set up, which you should stay for. So I didn't put all these examples in here, but I wanted to list like, we use this for harmful algal blooms. We use this for tracking flood damage. We use this for predicting flood damage. We use it for tracking hurricane damage. We use it for tracking urban heat effects. Urban planners use it. They can look at the development patterns in the past and model how they're going to change in the future. I mean, the list would go on and on and on, and it did go on and on and on, so it had to be pretty limited. But if you actually add all this up, and again, I'm not an economist, I did pull up this study. I tried to read it. I don't quite understand all of it, but it's estimated that just Landsat alone, which is one satellite mission, generates $25 billion in direct value to the United States. Again, I'm not super knowledgeable in the error when they do these things, but as I mentioned before, I sometimes argue with people online that I shouldn't, and one guy said, well, I bet they're off by 50%. And I was like, okay, I'll give you, let's assume they're off by 50%, so it only generates $12.5 billion. Like, this is, you know, this is huge. Yeah, so, and their operating costs are $130 million, so I forgot to do the math in there, but if you want to do the math and tell us what the return of investment is, it's pretty high. Not to mention that beyond, like, I don't think everything should be measured in a dollar value. There are so many projects where, you know, we worked with other countries, and I will go on a quick side story. So, as I mentioned, I was a field biologist. I got into this work because, as I mentioned, I was the one that could turn on the computer, and even though my title was like field supervisor or something, I found I was doing less I was in the field like one day every 3 months, and I was always on the computer. So I said, maybe I should try to get a job in this field, because as much as I like being a field biologist, I'm not that, but I'm still paid like a field biologist. I found this awesome program called NASA Develop that I joined in there. The whole purpose of that program was to take ologists of all different kinds, agronomists, biologists, soil scientists, urban plant health, people in public health, everything, and teach them how to use these tools. And in that, like, I was able to work with the Chilean embassy. We helped them map their wildfires. There were other people doing like famine forecasting in sub-Saharan Africa. So back to that point about dollar value, these projects that come out of these data often, first they can save human life, they also just generate goodwill between us and other countries. I used to like really talk this program up and try to get anyone that's in earth science or biology to join. Unfortunately, it was also discontinued last fall. So, but anyway, so going back to that, is it worth it? I can't tell you that answer, but I did pull up the budget numbers. So earth science is only 8.4% of NASA's budget. And earth science has a lot more than just satellites. So if you look here, I think like these missions, it's a very small part of earth science. And I'm using the 2024 data because I was actually having a hard time finding accurate data for recent years, because it seems like the accounting just isn't what it used to be. But I think, so if you look in psychology literature, like humans have a really hard time understanding large numbers. There's actually some really cool anthropology work where they found that humans innately think on the logarithmic scale. So we know at 1, we know 2 is twice as big as 1, and once you get beyond like 10, we kind of just operate on this thing like, well, 100's a lot more than 10, 1,000's a lot more, and I'm not saying that today, like now we learn numbers in scientific method, or scientific notation, but this is when they go out to like hunter-gatherer societies. The reason I'm saying that is, it's really hard for us to intuitively understand numbers. So I was like, okay, I think answering the question, is it worth it, we have to know how much does this cost relative to what we're paying. So if we have one tax dollar, everyone pays a different amount of tax dollars, but in a hypothetical single tax dollar, how much do you think is going to the NASA Earth Science budget? And I've created 100 grid cells, so those each represent 1 cent or 1% of a tax dollar. Any guesses?
1 cent.
That might actually be very hard to see, so for those in the back, to point of reference, I put it over George Washington's eye. That is NASA Earth Science budget. Before I gave this presentation, I did talk to my supervisor at the nonprofit I work at, and he said don't get too political, so I had the grand idea of like putting other projects in here, but I didn't. I would encourage you to do that exercise on your own. But then let's look at like the one satellite I used that actually last year they were talking about cutting, and I called our representative's office and they didn't even know what it was. They're like, what are you talking about, this Landsat thing? Any guesses, knowing that it's just a subset of Earth science?
One nose hair?
Basically, yeah. So it actually didn't really register as a pixel. So I put it on a penny, and for those of you in the back, it's still too small. I tried to keep the image to scale, but you can't interpret it. So we have to blow the penny up. So that is how much of your tax dollar is going to Landsat. We think of all the benefits. Like for me personally, that is worth it. I can't answer that question for you, but I hope I've given you some information that helps you consider that question and arrive at your own answer. Then, so when I was doing the NASA program, I love memes. I'm not, even though I say it on a computer all day, I'm not a gamer. My free time, I'm not on a computer too much, but I do love memes. I work for NASA. There was a whole series of these memes that would get sent around the office. Some of them got a little more ridiculous, like Starship Trooper type stuff. But the reason I wanted to share this one is because it is a joke, you know, like, oh, we could do so much. But this one, like, it's obviously utopia on Mars or something. And I think that's such a, this is a joke, so I'm fine with it, but it's such a short-sighted and narrow-minded view to think about, not just NASA, but US Geological Survey and NOAA and all these technologies, because, yeah, maybe they do cool stuff in space, but as I mentioned at the beginning of this presentation, Earth is the planet that is most studied by NASA. So really, I think if they had a budget the size of the US military, I think we would have cleaner water, less people starving, I mean, all sorts of really cool things. So on that note, I do need to save time for questions and the musicians, so I'll throw up my sources. There's 2 pages of them, so I'll toggle through so no one's left out. But I will open up for questions.
Would radar, like Doppler radar, be considered remote sensing?
Yes, I think that is on, if we go way back. And,
Repeat the question.
oh yeah, sorry, I'll repeat the question for everyone in the room and those on Zoom. Yes, would Doppler radar be considered remote sensing? And yes, that's one reason I didn't really particularly like that USGS definition. I should have just went to the Navigator page. It kind of left, I forgot how early it was in there. It kind of left that out. But if you see there, we've got Doppler radar. A lot of people don't think of these stationary things as remote sensing. By my definition, they are. And there are actually, we have another remote sensing expert. So I believe there are some satellites now using synthetic aperture radar. So they're actually sending radar down from space. I don't deal with that type of technology very often, though. Yes, I think, oh, well, either.
So thanks, that was great. We actually use your fire data that you guys produce to assess how well land owners are managing their land. So like farmers, ranchers, if there's an indication of fire on the land, it suggests that they are doing prescribed fire, they're doing good management on the land. And I've just been surprised by how much fire is showing up on, say ranch lands in your data, and I'm wondering if you have looked at that and if that makes sense to you.
Yeah, so 2 things there. First, I think that's a fantastic application. I tend to glance over that because when we got funding from NRCS, some of the people that get money from them, are they going to be spying? So that's the thing that also comes up. Are they spying on us? But it is a good application. Yeah, so I could give a whole talk, and next time I do, and I'll invite you all to look up on FNA, because there are errors with this. Our 2 big errors with this map are grassland and wetlands. That is an issue. We have a paper that, like I said, we work with U.S. Geological Survey, so once we write a paper, before we submit it to publication, they have to review it internally. It is now under U.S. Geological Survey review, so I'm hoping, you know, that's a government agency. It can take a little while, but hopefully by this fall we'll have that paper out, and what we provide there is a breakdown of our product by land cover type. And we actually were able to come up with a correction factor. And again, the 2 categories are wetlands and agricultural. So I don't know what would work for you on the specific tract, but if you're doing a broader scale study, like how much burning occurs in this county, you can then say, okay, well, 30% of this burning is in grazing land, so we know that this product overestimates grazing by 8%. I don't remember the exact numbers. The good news is in upland and even some not quite wetland, but wetter pine habitats, which is kind of the original impetus for this, it does perform pretty well. And then you had a question as well.
So can you tell the difference between prescribed burns and uncontrolled burns? You sound like my boss. That's currently my job. And the answer is no. It was no last year. It's still no. But hopefully, like maybe next year will be yes. So we can get to about 75% accuracy. Like I said, yeah. Like I said, this whole thing is, yeah. And this whole remote sensing idea is like you get that 75, and then there's all sorts of graphs and stuff you can look at. And I'll let you jump into because he is a remote sensing expert as well. But so we have some ideas to correct that, but it takes a lot of time, so I haven't gotten there.
If anything, a prescribed price should be a lot lower intensity and burn severity. If it's successful, it doesn't get out of hand and start becoming a canopy fire. So the first cut is like, well, this one's a little understood.
Yeah, so some of our predictors are severity, using the severity, but then that's a model product that we made. Severity, the number of property owners it crosses, the frequency of the thing is areas that burn once tend to burn again if they're being actively managed. If there's any burn permits nearby in that day. So it's like this whole range of predictors, and where I'm at now, I'm not, like, it's not anything I would try to publish, but.
The maps intentional would be more simple shaped, like squares.
Yeah, so.
Piece of property
So we were using some shape metrics, so like the ratio of the smallest hole, basically the smallest like sort of irregular circle you could draw around the shape versus the exact perimeter, because wildfires tend to like finger out more, but that's not always true in the southeast because we do a lot of burnouts where we just burn out the whole block. But like, yeah, that's exactly how we approach the situation. And really, I think the reason our estimate is low is not that the predictors are bad. I think it's the reason we have this project is because there's not really good data source. So the data we're feeding into the model are just like really messy. So if you put garbage in, I don't want to say garbage because a lot of partners have contributed, but if you put error-prone data in, you're going to get errors. So a lot of what I'm doing now is like manually going through. And I mean, Andrew has some good data. I went through all of it. His was awesome, except he spelled burn date a different way in each year. So, but no, I'm just ragging on him. But yeah, so I think it's more of a training data issue than the actual separating the two out. Any other questions? I don't want to run the musicians off. So
You're fine.
okay, cool. Thank you. Yes.
Is there a way online to go and browse through the data that you're producing?
Yes, actually I should have said that. Normally I have a QR code. So you can just Google Southeast Fire Map and you'll see it. It's free. The website's a little annoying because it's going to ask for your email address, so I just want to put out there that our government contract required that a web designer host it, not us, so you can blame them for the email. But we don't collect anything here to share. It's just for users. And then I think we had one question over there.
Is your work primarily, like, when you're designing models, are you doing more mathematical analysis, or is it software analysis? Are you writing code? Are you doing
Yeah.
spreadsheets? Like, what's the main...
Good question. I absolutely abhor spreadsheets. I think that most people, I like spreadsheets when they're just like displaying information. I don't like doing math or modeling in spreadsheets. I think most people in my field don't because, I mean, we have thousands of images for each tile, 31 years. I mean, it's hundreds of gigabytes of data. So the spreadsheet method doesn't work. It is a lot of coding. R and Python are two languages used in my office a lot, and it is a statistical model. So I use random forest and boosted regression a lot. And basically, those are kind of creating it's a mathematical way to create a bunch of decision trees. Like, think of, any sort of, you got a split in two choices. If the severity is greater than this, it's wildfire, otherwise prescribed, or otherwise we don't know. And you keep splitting down. And yeah, I'll be sticking around. So if you're like a student or something, have more questions, I can talk. But well, any other questions?
Just one last one. Do you use Google Earth Engine, or are you using other resources to get all the data together?
I was using Google Earth Engine early on. They changed a lot of their licensing, so for a nonprofit, it's not as affordable. And I could give a whole talk on like this field is weird because we have all this great technology, but it keeps finding itself in the hands of like private companies, and that's why, again, I'm a huge supporter of public data, public science, public resources. But yeah, we get our data. USGS just downloads it right from their server.
I just have one thing.
Sure.
And I know you know this, I think, but we put GPS collars on wild hogs, and we ended up using Southeast Fire Map to look at the areas that hogs were actually using and avoiding. And it was very interesting because they avoid places that have frequent fire, and they use places that should be burned but aren't being burned. And so it really pushed the prescribed fire message, and it was very useful for us. And also, when you work at Tall Timbers, you want everybody to burn, and so it just really pushed the message that prescribed fire is really important. And it was a good way to use the map, maybe not in a way that somebody thought about using, like with managing exotics, but it worked out really well, and it was a good thing.
Yeah, and I did know that, so I feel like a fool for not putting it in there. But also, I didn't want it to be like all Tall Timbers. But you should definitely come by Tall Timbers. There's a couple of Tall Timbers staff if you want to raise your hands, if you're brave enough. Talk to us. Come to our Fire Fest, and you can learn a lot. And
When
we're
is
not
Fire
just
Fest?
February 28. We do it every other year.
Every other year, so it's not this year, it's next year.
But the cool thing about Tall Timbers is we're not all just like nerds. Like Kim's out in the field almost every day. Andrew's literally driving a tractor and burning stuff every day. So we cover the whole thing from like space science down to
You're
like.
not a nerd, Chris.
I mean, everyone here's it. If you're at a science event, but yeah, I don't want to take the musicians' time, so I'm going to unplug. But I will be here for like you can ask me any questions. Thank
Okay, yes, please join me in thanking Chris and thanking Blue Tavern and Carrie Hamby for hosting us. And you guys probably already thirsty, so please talk to Isabel. She may help you with that. And then if you want to know more about what Tallahassee Scientific Society does,